We'll discuss on structural health monitoring with artificial intelligence for structural engineering. Myself, Dr. Shyamal Guchhait. I am assistant professor in the Department of Civil Engineering in NIT Rourkela. So first of all, the second slide, it is related to the overview of my presentation. So I'll be discussing different techniques related to SHM, structural health monitoring or structural damage detection. I'll start from the traditional gradient-based optimization methods. Then I'll discuss about error in constitutive equation-based approach. And after that, I'll discuss the damage detection of the truss structure with PSO, particles from optimization. And at the last, I'll discuss the convolution neural network-based damage detection technique with time-domain vibration data. So first of all, what is structural health monitoring or structural damage detection? Basically, these two are almost same. Structural health monitoring, it is an actually superset, you can say, and structural damage detection, a part of it. Okay. So structural health monitoring, we can call it in different way. Structural health monitoring or structural uh, damage detection or structural condition monitoring. Different terms are there. So first of all, we can perform the structural health monitoring or structural damage detection with different techniques. We can perform NDT testing. Okay. Like for concrete, we can perform ultrasonic pulse velocity test or impact hammer testing. Okay. By that, we can detect the damage position. And second is the inverse problem. Inverse problem means it is related to optimization techniques. We can apply different optimization techniques to find out the damage location, as well as we can quantify the damage also. Inverse problem, actually it is to find out the means if we have the behavior pattern of a structure and with this inverse problem we can predict the actual cause. So two problem we have to solve for solving and for detecting the structural damage with inverse technique. First we have to solve an forward problem, which is you know very means for standard static case the equation is Ku equal to F, where U is the displacement field, K is the stiffness matrix, and F is the force. So if we know the load boundary condition material parameter, we can solve easily and find out the displacement field. So this is all out of forward problem. And what about inverse problem? Inverse problem means we can identify, means if we know the boundary condition, if we know the load property, load on the structure and the displacement field, then inversely we can identify the material properties, means material or geometrical properties. So that is the inverse problem. Can you hear me?
Yes, it's fine.
Okay, okay. So means inverse problem, it is very much important to solve a structural health monitoring problem or structural damage detection problem. Okay. Now first I will define uh, the structural damage detection, SD detect. What is structural damage detection? Actually, damage, it can be defined as the deterioration in the structural original geometrical property or material properties, and which will lead to the failure of the structure. So there are 4 steps for the structural damage detection. First is finding out the existing of the damage. Second is to locate the position of the damage. Third is quantify the damage, and fourth is the remedial measures. Generally we'll follow the first 3. Okay. The remedial measures, it is related to that retrofitting and rehabilitation of the structures. So in the structural damage detection, we generally follow the first 3, finding out the existing of the damage is present or not. The second is to locate where the damage has happened, and third is how to quantify the damage. Now in this figure, you can see there are 2 kind of damages. Figure A actually, it shows the corrosion in the steel structures, and figure B, it shows the crack, how the cracks develops in the concrete. So both figures actually it is related to the damage in the structure, either in steel structure or in concrete structures. Now, in this slide, you can see there are means I have already told you there are different kind of methods we can apply for structural damage detection. First is the traditional verification techniques. See the traditional verification techniques. Okay. Now in the traditional verification techniques, there are two methods. One is visual inspection and another is non-destructive text. In this figure also we can see means surveyors are performing visual inspection on a steel structure. And we can also perform after that, after the visual inspection, next step is the non-destructive test, means performing NDT testing on the structures to find out the degrade behavior of a structure. The next is optimization based method. In optimization based method, we can have image based method or the vibration based method. Vibration based method means that we will use the vibration data, either natural frequencies or mode shapes, or we can use the time domain data like acceleration, velocity, displacement. Okay. And you can see here in this image also a drone, it is used to collect the raw images from the structures, and these images, with these images, we can means perform the structural damage detection and identify the damage position as well as quantify the damage. Now, in inverse identification techniques, we have the conventional optimization methods. In the conventional optimization methods, we can first means the traditional, the first very basic part means very basic methodology. It is the direct search methods like simplex search method. It is an example. The next category, it is the gradient based methods. Gradient based method, like I think you have heard those names, that Gauss-Newton method or quasi-Newton methods. These methods are related to finding out the gradient and the Hessians. And that next part, it is the latest, that artificial intelligence based algorithm. Actually, AI, it is the superset. Okay, from this figure, you can see that AI, it is the superset. Under this machine learning technique comes, and neural networks, it is the subset of the machine learning, and ultimately the deep learning, it is the subset of neural networks. So the whole means AI covers the whole picture. Now in machine learning techniques, we can use different techniques like gradient, like GA, okay, or PSO, particle swarm optimization. About PSO, I'll discuss today, and then we can means have the neural networks and ultimately deep learning techniques. Okay, the latest one. Now, first I'll discuss with that traditional method, gradient-based optimization method. In the gradient-based optimization method, our target is to reduce the error functional or objective functional. Okay, and here you can see the objective functional. It is the second knob between the calculated displacement and the measured displacement. Here U, which is a function of beta. Beta means the material parameter or geometrical parameter. It is the calculated displacement, and UM, it is the measured displacement. So basically, we are calculating the error between this calculated and measured displacement, and with that gradient-based techniques, we are trying to reduce this error. Okay. And here R is an regularization functional. We generally use the regularization functional where the noise is there in the measurement. Okay. Now there are different techniques in this gradient-based method. If we want to use the Gauss-Newton method, then we have to also calculate the Hessian. Okay, but to calculate it, it will be computational cost will be high compared to the quasi-Newton, means gradient-based method like quasi-Newton method. Okay, so there are two kind of methods in this. One is Gauss-Newton, which is where we have to calculate the Hessian, and in the quasi-Newton method, we don't need to calculate the Hessian. The cost will be also reduced. Okay. The main disadvantages of this L2 minimization approach, it is that this error functional of the objective functional, it is non-convex. Okay, and this methodology or these techniques, it is very sensitive to initial guess values. If we choose wrong initial guess values, then our solution will converge to local minimum. It will not converge to the global minimum. Now another technique it is there. Here it is called error in constitutive equation based approach. In this technique, actually it is a Lagrangian based approach. Here we are using a different cost functional. Okay, we can see here the cost functional. Here, actually, the cost functional, it is calculating the error between in the constitutive relationship. Okay, here the stress sigma we are calculating with the numerical data, and the strain epsilon we are calculating with the experimental data, experimental displacement. Okay, measured displacement. So there will be an error, and with this optimization we will be trying to reduce the this cost function or objective function. So in any optimization technique, our target is to reduce the objective function. Now this EC actually it is a very means it have a very physical significance meaning. Okay, and it is directly related to the constitutive relation, but uh, in the real field, noise will be there in the measurement data. So in that case, we cannot use this EC technique, error in constitutive equation approach. We have to use a modified EC, which is called MEC. Okay, there will be two terms. One will be the error in the constitutive equation, the first part, and the second part will be the error in the measurement. Okay, the second part, it is related to the error in the measurement. Error in the measurement means we are taking here the error between the calculated and the measured displacement. One important thing it is that here that we are actually the second part, it is actually a penalty term. Okay, here alpha it is the penalization parameter, and you can see here that if alpha is tends to 0, then we means MEC converges to EC, and if alpha tends to infinity, then MEC technique converges to the L2 minimization error, the first which I have discussed. Okay, so and with this modified MEC technique, actually I have verified. I am so you can see here the damage detection of the isotropic aluminum plate with the experimental data. Okay, means the EC modified EC techniques has been used to detect the damage position with the experimental natural frequencies and mode shape data. Okay, so you can see here the in this figure the experimental setup of the damaged cantilever aluminum plate. Okay, and the plate size it is 250 millimeter cross 400 millimeter, and the thickness is 4.8 millimeter. This square portion, okay, in this middle of the plate, we have taken some remove some portion, okay, and we have artificially created the damage. So that damage dimension, it that means we have taken 2 millimeter thickness from this squared zone. Okay, so the damage index it is 0.583 for this portion. Now our target is to detect the damage position with experimentally find out natural frequencies and mode shapes. Okay, so how to do this? Next lab we can learn. So before doing this, first we have to perform some standards test to calculate the means density of the material. We have taken the aluminum, so we have performed and we have find out that the density it is 2697 kg per meter cube. Then to means we have found out a Young modulus and the Poisson's ratio using the UTM machine for these dog bone samples, and these samples has been created with means following the ASTM E8 standard. Okay, ultimately we have got the value of the Young modulus, which is 7.715 GPa, and Poisson's ratio it is 0.326. Next, we have performed the experimental modal analysis, and you can see in this figure the third mode. The first means that figure A, it is showing the numerical part, and figure B, it is showing the real part of the experimental mode shapes. Okay, and you can see that comparison between this third natural frequency, the experimental frequency, it is 142 Hertz, and numerically means it is modeled in the MATLAB, and we have got the third natural frequency, bending natural frequency as 155.27 Hertz. So there is an 8.55% error. Obviously, there will be error because means there will be error between the numerical and the experimental natural frequencies as well as mode shapes. If you perform experiments, there will be some error. Now we have used that MEC technique to find out the damage location. So in this figure, you can see that reconstruction of the damage index for the 10 into 16 mesh that plate element. And A figure, it is shows the reference damage. Figure B, it is the present MEC method, and C is the standard MEC method. Okay. So with our proposed EC technique or modified EC techniques, we have means we can identify the location as well as quantify the damage also. Okay. So we can successfully identify the damage with EC technique. Now, in the next part, so first I have discussed that we have started with the traditional one, gradient based techniques. Okay, then we have discussed another technique, Lagrangian based approach, optimization approach, which is called ECE, and modify that MEC or modified EC. Then we'll come we'll discuss a global optimization technique, which is called particle swarm optimization. This particle swarm optimization, it comes under the evolutionary algorithms. Okay. So, and we will be discussing how to detect the damage of the truss structures with the PSO technique, particle swarm optimization technique. This particle swarm optimization technique, it is a stochastic global optimization technique. Okay, and it is first proposed by Everhart and Kennedy in 1995. After that, lot of researchers and scientists have used this PSO technique in different problems, not only in structural damage detection problem, but for other optimization problem also, like shape optimization or geometry optimization of truss structures or any kind of steel or concrete structures. It has been used in civil engineering field. In other field also, means in economy or mechanical sciences, we can use PSO. Okay, it is a global optimization technique. So it is not dependent on the initial gauge values. Now I'll be discussing that one problem related to damage detection of the truss structure. So I have taken the results from this paper. Das and Dhang 2020. They have proposed a self-controlled multi-stage PSO technique for identifying the damage using the particle swarm optimization technique. Okay. So this multi-stage strategy, it is developed to eliminate the healthy elements and reduces the dimension of the search space in each stage of the method. That means in multi-stage strategy, what they have used, they are reducing the number of variables. Okay. In any optimization techniques, if you can reduce the number of variables, then that ultimately your algorithm will converges very fastly and the result will be very highly successful. Okay. So in objective function, we are using both error in the natural frequencies and the error in the mode shapes. Can you get my slides?
Yes, yes.
Okay. So we are discussing about the the damage detection of the truss structure with PSO. So here you can see there are two parts in the objective function. One is that error in the natural frequencies. Okay. This omega n, it is showing or it is representing the calculated natural frequency. Okay. Means with some coding. We can do the coding with MATLAB and other software also. Okay. And WE or omega E, it is actually representing the frequency, natural frequency, experimental natural frequency. Okay. So the first part F1, it is related to the error in the natural frequency. Okay. And N is what? N is the number of the natural frequencies or mode shapes we are considering. Okay. The second part, the F2 part, it is related to the error in the mode shapes. And we are calculating the error in the mode shapes with a number which is called modal assurance criteria, MAC value. Okay. So basically MAC is what? It is giving the correlation between the two sets of the vector. You can see here the phi a and phi x. So you can say phi a, it is the calculated mode shapes, and phi x is the experimentally measured mode shapes. Okay. So if you do this, you will calculate the relation or correlation between these two mode shapes. Okay. So with this MAC value, we can calculate the F2 function. and then we'll be using both two, error in the frequency and error in the mode shapes. Okay. Omega I, it is the means here n it is for numerical, e it is for experimental. Omega I means the ith natural frequency and phi I means the ith mode shape. Now what we are doing here, that error function, it combines of two parts. What I have already told you, that f1x and f2x multiplied by the two factor alpha and gamma. Okay, so these are the two weighting factors, and for this present study, actually they are taking the value of alpha, it is 0.01, and gamma it is 100. And what is x here? X actually it is the damage variable vector containing the damage severity. So damage severity, it it is having the range from 0 to 1. Okay. So 0 means no damage and 1 means fully damage. And in between, if we have say x equal to 0.2 for some particular member, so that means 20% damage happens for that structure. Okay. So this x, this vector, it is actually our variable in this algorithm. Okay, we have to find out the x. Okay, we have to minimize the effects. So the optimization problem we can define here. You can see that we have to find this vector minimizing the fx, that cost function or objective function, and subjected to some criteria. So x should be greater than equal to xl and should be less than equal to xu. So xl means the lower limit of that damage vectors, and xu it is the upper limit of the damage vectors. Okay. So lower limit it is the 0, and upper limit we have set, or they have said in this algorithm, that is 0.9. Now with this damage detection of a 25 bar planar truss has been performed. Okay. Now in detect the damage, there are 3 damage cases they have taken. Damage case 1, damage case 2, damage case 3. In the damage case 1, only one member has been associated with damage, 20% damage. Okay. In the damage case 2, there are, means the damage has been provided for the 2 members, 1 and 12, 10% and 30%. And in the damage case 3, 5 element it is chosen, and the damage percentage also varies from 20% to 60%. And how the damage means it is created by reducing the Young modulus. So you can also reduce the cross sections, okay, like the thickness also. But in this paper, they have reduced the Young modulus. So damage in any member xi, it is defined as change in the Young modulus divided by the original Young modulus. U, it is the modulus, Young modulus of the undamaged member. EDI, it is the Young modulus of the damaged member. So by that way, you can define the damage. And the 3 damage cases have been defined. Okay. First damage case for only one member with 20% damage. The second damage case for the 2 member with 10% and 30% damage. And for the third case, 5 member with damage starting from 20% to 60%. Okay. Now 5 natural frequencies and 5 mode shapes has been considered for defining the objective function. And here they have used the means to simulate the experimental data. What they have done, they have first modeled, means they have find out the natural frequencies and mode shapes numerically, and then they have added some standard error function. Okay. With means for frequency they have added 0.15% of noise, and for mode shapes they have added 3% of noise. Okay. So and with this they have performed the damage detection analysis. Now you can see here the results obtained by that PSO technique. Okay. So for damage location, 3 cases are there: case 1, case 2, and case 3. So for case 1, exact damage severity was 20%, and if in that data, natural frequency and mode shape data, if noise has not been added, then the means the predicted severity is 20%. So there is 100% accuracy, and if we consider the noise in the measurement, then the accuracy it is reducing, but very less, 19.91, so almost above the 90%. Okay. For the case 2 also, you can see that if we don't consider the noise, then the prediction it is 100% accurate. Okay, and if we consider the noise, then there is some error. So for single damage case and as well as for the multiple damage case also, this PSO algorithm, it is detecting the damage position and also quantify the damage very accurately. Okay, so for no noise case, 100% accuracy it is maintained, and for if noise is there in the measurement, then some error it is there. For almost means for all the cases, the accuracy is more than 90%. If you calculate, it will come. I think even 90, more than 95%. So we can see by the same result with this figure that in this figure it is showing that damage positions, means how this algorithm is detecting the damage. Okay, that actual damage, predicted damage without noise, and the predicted damage with noise. So for uh, damage case 1, all the cases the accuracy is very high. Okay. Now this figure it is for the second damage case where two members means have been means damage has been created to for two members, and you can see that PSO algorithm it is very successful for detecting the damage without noise case and with noise also. Okay. Already we have seen in that the results in that table, but now we are seeing it graphically. Okay. The third case where the damage was for the 5 members, and you can see here the same thing that the PSO algorithm is very successful for detecting the damage. Okay, for multiple damage case. Here the 5 damage cases are there. Now, till now, we have covered the gradient based method. Then we have discussed about the error in constitution based approach. Okay. After that, we have discussed that heuristic method or evolutionary technique like PSO. Okay, for damage detection case. Now we'll be discussing about the latest technology like deep learning technique like CNN, convolution neural network. Okay. Now, the conventional damage detection techniques, it is actually the very laborious and time consuming, expensive, because either we have to perform the visual inspection or we have to perform the entity testing. Okay. The current literature, which shows the parametric approach, here we can use the modal and time domain data, but that important features we have to capture by the machine learning technique. Okay. Means if we use the machine learning technique like PSO or GA, we have to provide the important features, okay, manually. But with this invention of the deep learning technique, okay, that automatic feature extraction capability, it is means it's developed. Means the deep learning algorithm has the capacity to detect the sensitive features automatically. Okay, so that is the advantage using the deep learning algorithm. Okay, and with this deep learning algorithm, we can detect the internal damages. So that's why you can say that it is very much suitable for online structural health monitoring. Okay. In this figure, you can say that example of an online structural health monitoring. You can see here a bridge is there. Okay. A bridge is there, and in this bridge, some sensors are there. Sensor means accelerometer or displacement meter. You can put anything. Okay. Now, from that sensors, from that accelerometer or displacement meter, you can collect the data very means time to time. Online, you can collect the data, and after that, you can store those data in the data acquisition system. Okay. After that, this data from the data acquisition system, that the data it is transformed. I mean, it is transferred by the some communication system, means wireless systems. So by wireless system, we can transfer this data, and it will be received by some data processing system. Okay. And after that, in that data processing system, we can use some algorithms, damage detection algorithms, okay, to detect the position as well as to quantify the damage. Okay, so this is the whole procedure for online health monitoring. So it starts from the collection of the data from some actual structure like bridge or any other building structures. Okay, so we can collect the data. then the data will be transformed to the data processing system, and in that from that data processing system, we can take the data and with some server, means with some computer or even laptop also, we can perform the damage detection procedure with some algorithm. Like we can use the deep learning technique, or we can use the any global optimization technique like GA or PSO. Okay, so generally nowadays this deep learning algorithm, okay, or you can also say that convolution neural network, it is a deep learning algorithm, okay, type of deep learning algorithm we can use to detect the damage, to perform the diagnostics. Now in this slide, we will discuss about the convolution neural network. So convolution neural network, actually it is a multi-layer neural network. Okay. And it is designed to recognize the pattern from the images or time domain signals. So images means we can collect the raw image data using drone, or manually we can take the image data from cell phones or other digital camera. Okay, so that data we can use either, or we can feed some sensors. So in that previous figure also we have seen that in that actual structure some sensor has been placed as some accelerometer. So from that also that sensors we can collect the data, acceleration data or the displacement data. Okay, so so it can design, means it is designed to recognize the pattern directly from the images or time domain data with optimal pre-processing. Okay, so means very optimal pre-processing it is required for convolution neural network. Okay, now in this figure you can see the schematic diagram of convolution neural network. So first of all, some input will be there either in the form of image or time domain data. Then the CNN, it consists of some convolution layers. Okay, so convolution operations will be going on with this input data. Okay, and that convolution layers, it may be a single layer or it may be a multiple layers. Means we can add 2 or 3 layers depending upon our, means depending upon our the size of the optimization problem. Now, after that, the data means from the passing from this convolution layer, it will pass to pooling layer. Okay, so we can use either means average pooling or max pooling. Okay, for reducing the data. Okay, and after that, this data will be transferred to the fully connected layer. Okay, this fully connected layer actually it consisted of MLP, means actually multi-layer perceptron, means ANN it is there in the fully connected layer, it consists of some layer of ANN. Okay, and after that the output will be generated. So this is the total schematic diagram of the convolution neural network. Now actually we are using with my PhD student, we are doing the structural damage detection with this CNN technique, with 2D CNN. Actually, CNN is convolution neural network, and we can perform this CNN convolution neural network either taking data as an 1D array. So that is called 1D CNN. And if we take the data means the image data or the time data as in 2D matrix format, then it is called the 2D CNN. Okay. So 1D CNN, it is very popular for time data. Okay, damage detection with time acceleration data, and 2D CNN, it is very popular in the field of damage detection with image data. Okay, so but there is very few study which actually use the 2D CNN for time data. So in the we have published a paper, okay, in this topic, the damage detection of steel structure with 2D CNN, and we are proposing here a 2D CNN technique for time domain data or damage detection using the time data, okay, time acceleration or displacement data. Now you can see here a cantilever beam. Okay, in this beam, there is total 15 number of elements that this beam, it is modeled in FEM software Abacus. Okay, and at the right hand side, and instantaneous load it is given to generate the, it resembles the dynamic load to generate the dynamic data or time domain data acceleration for all these node points. We are providing or we are applying an instantaneous dynamic load, okay, on this beam. And how the damage it is created by reducing the thickness, okay, for different element, okay. A schematic diagram of the cantilever beam with sample damage it is shown here. So that sample damage it is created on this fifth element. We have created, means we can create the damage for other elements also, but in this figure it is shown only for the fifth element. Okay, and you can see that table one, the different property, that density it is 7850 kg per meter cube. So it is a steel beam. Modulus of elasticity it is 200 GPa. Poisson's ratio it is 0.3. The damping it is considered the Rayleigh damping, mass and stiffness proportional damping, 2% Rayleigh damping for steel structure, and that damage it is created by reducing the thickness from 10 to 50%. Okay. And load it is we have already, I have told you that we have used the instantaneous load to generate the time domain acceleration or displacement data. Okay. So this figure it shows the operational procedure of two-stage 2D CNN algorithm. Why two-stage means we can perform the damage detection in one stage also. Okay. Generally, we find the papers like that way, that they have used only one stage 1D CNN algorithm to detect the damage. But uh, if the number of variables it is large, so that will be difficult to use the one stage algorithm to detect the position and quantification purpose. So because of that reason, we have used two stage algorithm. In the first stage of the damage algorithm, we are uh, detecting the location, and then in the second stage of this CNN algorithm, we are detecting the, or we are quantifying the damage. Okay, so Google Colab platform, okay, it is used for writing all the codes of CNN. Okay, and in the Google Cloud platform, we are importing the data first. Okay, then calling the simulated data set for location identification. After that, we are splitting the data. Okay, for training and testing part. Okay, then after that, we are doing the training and testing, and we are using the 2D CNN algorithm to detect the location of the damage position. And with this data only, then we are moving forward to the second stage algorithm, okay, that we are calling the simulated data set of already identified damage locations. So we are in the second stage, we are only using the data of the damage locations identified already. And then after that, we are following the same path, means we are using the 2D CNN algorithm. Okay, and then we are detecting the damage position. And after that, we are generating 2D or 3D bar charts to show the accuracy and the loss function for the CNN algorithm. So this is the overall procedure for detecting damage with 2D CNN or two-stage 2D CNN algorithm. Now, in this figure, you can see that validation accuracy of the proposed 2D CNN model for the cantilever beam problem, and that means that data, okay, that measurement data, it is generated synthetically. So we are adding some noise to make it synthetic measurement data, and we are adding some Gaussian random noise, okay, in different percentages, like 1%, 2%, 3%. So you can see in this figure there are four curves. One is nil noise, means no noise, and other three it is for 1%, 2%, and 3% noise. Okay. So from this graph, you can see that if noise is not there, almost 100% accuracy you can achieve. Okay, and with very less iteration. So up to say 100 iterations. Okay, and if we increase the noise, then the accuracy is decreasing, but the overall accuracy, even if we consider the 3% noise, then the accuracy we are getting more than 80% or around 85%. So this figure it is showing the single damage detection scenario. Okay, for the seventh location of the cantilever beam. So the beam has been divided into total. You can see from this figure total 15 number of element. Now we are creating the damage in the seventh element. Okay. So the seventh location, it is means damage occurred at the seventh location of the cantilever beam with 25% severity. Okay, so at the seventh location we are giving, means we are reducing the thickness of 25%. Okay, now the first stage, you can see that our algorithm is easily quantifying the location of the damage with 0%. The left side figures, it is indicating the 0%, the result with 0% noise. The middle column, it is indicating the result with 1% noise, and the right side, the third column, it is indicating the results with 3% noise. So for all the cases, you can see that accuracy prediction, okay, it is almost 100%. For the location detection, the first row, it is showing the location detection, and the second row, it is showing the damage severity, the second step. Okay, so for both cases, the accuracy is almost 100%, and you can say that if we consider the 3% noise, then the accuracy is coming more than 99%, 0.992, that means 99.2% accuracy for the detection of the damage severity. Now this is the multi damage scenario case. That damage occurred here at the 3 simultaneous location. Okay, so we have, I mean, firstly, we have given the damage for the only one element, the seventh element. Here we are creating the damage for the 3 element, third, fifth, and eighth. Okay, and it is not, means same damage severity, it is not there. For the third element, we are giving the 10% damage severity. For the fifth element, 20% damage severity it is considered, and for the eighth element, 25% damage severity we are considering. Okay, so the first row, it is showing the, means how the algorithm is successful to detect the location of the damage. Okay. The first figure, the left hand side figure, it is showing that accuracy with 0% noise, and the right hand side figure, it is showing the accuracy with 1% noise. Okay, for detecting the damage of 3 positions, third positions, third element, fifth element, and the eighth element. And next row, it is showing that how the CNN algorithm is capable to detecting the noise. Okay, the accuracy, it is shown for detecting the damage severity. So the first row, it is the location of the damage. The second row, it is the damage severity. Okay, for the 3 positions, third positions, fifth positions, and the eighth positions. And the percentage of damage is 10%, 20%, and 25%. Okay, so this figure, left hand side figure, it is showing the prediction of damage location and severity for 0% noise, and the this right hand side figure, it is indicating the prediction of the damage severity with 1% noise. So you can see, if we uh, go for the damage detection for the multiple damage location and with multiple severities, then there will be some error. Error means here there's some percentage. It is very less also, though, that means other location is also identified. Okay, we are giving the damage in third, fifth, and eighth, but here some means in the eighth location, some means other percentage it is also coming. Not only the means 10, 20, and 25, other percentage it is also coming. 20% it is also coming. Okay, so this portion, it is indicating some error, but this error, it is very less. Now, so this is also related to the damage severity of multiple location. Okay, so here also multi-damage scenario case, damage occurred at the third simultaneous location with different severity. Here also we are considering that means the damage at the different locations, okay, with different severity. And you can see that if we consider the multiple damage location, then there are some erroneous results. Okay, when there is some noise, if you consider the 3% noise case, then you can see there are some small bars are coming. Okay, although the errors it is very less, means very close to zero, but error are coming if we consider the noise. Now, lastly, that we have validated our proposed two-stage 2TCNN technique with the experimental data. Okay, and that is means that is taken from this. Means we have performed this experimental validation on this QSGS data, experimental data. Okay, so what it is there, that QSGS means Qatar University Grandstand Simulator. Okay, so in that Qatar University they have created a steel frame. So this steel frame, it is having 30 members, 30 steel members. Okay, and total number of joint is 30. Means actually total number of joint is 30. So there will be 20. And some steel members will be there, and the total number of joints it is 30. Okay, so basically it is a steel frame. Okay, and how they have created the damage? For every position, one by one, they have loosened the bolts of these joints to create the damage. So the implementation of damage, it is created by loosening the bolts of the joint position. And the data, it is collected by using the accelerometers provided at the joint position. So joints, the damage it is created by loosening the joints. That is the important thing. And the second thing is that the data, it is collected by the accelerometers putting at the joints. And we have used actually this data, it is available in their site. Okay, and we have taken this data and validated our algorithm to means that 2DCNN algorithm. Okay, so this validation accuracy means you can see this validation accuracy plot and the loss plot. Okay, two plot it is there. The left hand side plot it is showing the accuracy plot. Okay, and the right hand side figure it is showing the loss plot. Okay, so and we means we have compared our results with different other deep learning techniques like CGRU. Okay, 1D CNN technique, DNN technique, and GRU technique. So you can see the comparison plot here. Okay, so means that if you look this first plot, that convergent history of the accuracy, you can see that our proposed 2TCNN techniques, it is taking very less iteration, only 8 to 10 iteration to accurately detect the damage, and the accuracy it is almost 100%. Okay, with only 8 to 10 iteration. But for other algorithms, if we consider the 100 iteration, 100 number of iterations, the accuracy it is coming almost 90%. Okay, and in that second figure, that right hand side figure, you can see that convergence history of the loss. Okay, loss functions we are plotting. So that y-axis it is showing the average loss, and the x-axis the epoch or iteration. And you can see here also that with 8 and 10 iteration, our algorithm means for our algorithm, the loss it is reached to 0. Okay, and for other algorithms, that it is taking say lot of iterations. Even after 100 iterations also, the value of the loss functions, it is not coming to 0. Okay, so we can see that that our proposed 2TCNN algorithm, it is very much capable of detecting the damage positions for numerical case. And we also validated our algorithm with this experimental data of the means actually data collected from the experiment. Okay, on steel frame. So the next slide actually means it is showing that how our algorithm it is capable for detecting the damage. First figure it is showing that how that means how that algorithm it is detecting the damage for the seventh joint. Okay, you can see the accuracy is almost 100% for the seventh joint. Okay, this all means for three cases we are considering. That's on the damage occurred at the seventh joint, damage occurred at the three simultaneous locations, and damage occurred at 5 locations simultaneously. Okay, so for all the three cases detecting the damage we are using the experimental data only. The data which means that means what they have created. Okay, that data, acceleration data only we are using. And with that data also you can see that not only for the single damage case, for multiple damage case, means for damage detection of 3 locations and damage detection of the 5 locations also, the accuracy it is coming more than 99%. Okay. So it is very much capable of detecting the damage locations uh, with QSGS steel frame data. So lastly, these are the references, means I have discussed about this paper very in detail, that Das and Hang et al. Okay, and other details are there. So you can see this is all about the presentations using means of structural damage detection using AI. So we have discussed a detailed, means lot of procedures starting from the gradient based techniques to, after that we have discussed the error in constitutive equation based approach. Next we have discussed a global optimization technique like PSO, particle sum optimization, and finally we have learned how CNN means, CNN means convolution neural network, which is a type of deep learning algorithm, how means this CNN is capable to detect the location for single and multiple damage case with no noise as well as noisy data. And ultimately the experimental validation is also has been presented in these slides. So if you have any questions, you can ask.
Participant, do you have any queries? So you can go for the demonstration part.
Yeah. So next part, actually, can you see that window?
No, still PPT mode. We are able to set a screen that.
Okay, okay.
Is,
Okay, then I'll again share. Okay.
yes, yes.
So is it visible now? The that
Yes,
MATLAB?
yes, yes.
Okay, okay. So now we'll start the second part, means we'll be here we'll be learning how to write and code in MATLAB to detect the damage for a cantilever beam. Okay. And we'll be using the natural frequencies and mode shapes only. Okay. So first of all, means first you have to familiar with the MATLAB. Okay. So I know that you all of you know the MATLAB because it is very basic. If you want to learn the coding, means that MATLAB will be the basic. Okay. So and you can write very means program very easily in MATLAB platform. Okay. Now in MATLAB, first you have to open the MATLAB. Okay. And you have to write that coding in script files. Okay. So I have written this coding of detecting the damage of beam structure, cantilever beam structure. Okay, in separate script files. The main files, it is the main. So I have opened this main.m. .m is indicating the MATLAB script files. Okay, so we can execute these files. Now to create this program, first of all, we have to start with some basic command. Okay, so there means in this platform, either you can means write some in command on this command window directly. Okay, say if you write 2 plus 2, then it will directly give answer 4. So that means it is acting like a calculator. in command window. Okay. So in command window also, if you means write program and if you run it, then also it will run. But generally the programmer will what they'll do, they first means write all the command in this separate script file, which is called .m file. Okay, for MATLAB. So here I have written all my coding in different uh, this script files. That main file, I have written the main coding. Okay. Now I'll start. You can see at the top, you can see some command like close all, clear all. So these two command it is related to, means if you want you want to run your coding from the start. Okay. So you should write these two command, close all and clear all. So that will clear the previous histories. Okay. CLC also you have to write, and this tick, and at the bottom at the last of this coding I have written talk. So tick tock, actually if you write it here, if you write this command, then it will show the total timing of the coding. Now after that, if you means if you have done coding, okay, for any purpose, then you know that you have to define some variable. Okay. In MATLAB, actually you don't need to define the variable automatically. If you write, it will define the variable. But if you want to declare some variable as a global variable means actually that scripting part, it is not written in one script file. It separate, means for several small activity we'll be writing some uh, other files, other script files also. Okay. So this is the main file, and after that, for other small purpose, you will be writing other script files. Okay, sub files you can say. Okay. So uh, now if you declare any variable as a global, so it will remain global for all the sub files. So that is the advantage of declaring a variable global. Either if we use the variable for this file only, main file only, then you don't need to declare the variables and the global. So I have declared here some variables as global because these variables will be used in other subfiles also. Now there are some other variables like LCase. LCase 6 means we will be using total 6 natural frequencies and 6 mode shapes. Okay. So total case is 6. LX equal to 1. LX indicates the length of that beam. So unit it is 1 meter. Okay. Or you can, in any unit you can take. Breadth and depth of the beam, it is taken 0.2 and 0.2. Okay. So that means 0.2 meter depth and 0.2 meter breadth. Area, it is breadth into depth. NX 30 means the total 30 number of elements I have taken. Okay. And nodes will be NX1 equal to NX plus 1. Okay. So total nodes will be 30 plus 1, 31. Degrees of freedom, as I am taking the beam element, so the NDOF means degrees of freedom per each element. So that I have taken 2. Okay. And any element is total number of elements. So total number of element equal to NX means 30. Okay. Now after that, declaring all these basic variables, after that for finite element coding, we are generating, our target is to first generating the stiffness and the mass matrix. Okay. For the each element, then we'll assemble the stiffness as mass to form the global stiffness and global mass matrix. After that, we'll be solving the eigenvalue problem. That problem is that k minus omega square in bracket k minus omega square m in bracket into x equal to 0. Okay. So that free vibration problem will be solving to get the free vibration problem or eigenvalue problem, you can say, to get the natural frequencies and mode shapes, omega and the x vector. Okay. So for this case, we can generate means any number of natural frequencies and mode shapes, but here we'll be using only 6 natural frequencies and mode shapes. So that's why I have at the start I have written that LK is equal to 6. Now next, what we are creating? We are creating the connectivity. Okay. Here you can see that some lines has been written with percentage sign. So if you write a line with percentage sign in MATLAB, that line will not be executed during the means run. If you run this program, these lines will not execute. So to means for your own clarity, okay, and to understand the coding very easily, you can write some unexecutable lines, okay, such that you can means, uh, means you can learn, okay, or you can no, means you can learn the algorithm very clearly. So here the generating connectivity and coordinates, it's this line, it is written with this percentage sign. Okay, so that means this line will not be executable. Okay, other lines will be executable. So to generate the connectivity, we are what we are doing here, we are running two loops. Okay, so this for and end, for loops, actually two for loops we are generating. Okay, means two for loops will be running to generate the connectivity of the member. I know you means I guess you know that connectivity. Connectivity means that each element here a matrix will be developed where the first row will be the row means that element number. The second row will be that uh, that the first node of the each element, and the third row will be the second row, that second node of the each element. Okay. So there will be three row here. This connectivity matrix. The first row, it is indicating the element number. The second row, it is indicating the first node of the that each element, and the third row will be indicating the second node of the each element. Okay. So connectivity it is needed in FEM to generate what? To generate the elements means that global stiffness matrix. From element to global, if you want to generate the that global stiffness matrix or global mass matrix, you need that connectivity. Okay, connectivity between the elements. Then after that, we are generating the coordinates. That coordinates of all the node points, it is generated and it is stored in this coords variable. Okay. So for each node, the coordinates will be generated and it will be stored in this coords variable. Okay. So that connectivity portion we are generating. After that, we are generating coordinates. Then we need to generate the boundary condition. Boundary condition means here the cantilever, for this cantilever beam problem, the boundary condition is at the left hand side, the node is fixed. So the degrees of freedom, the first and the second degrees of freedom will be restricted. So that we are creating with this variable fixed nodes. With these fixed nodes, we are providing that the first degrees of freedom and the second degrees of freedom of the node 1 will be having value 0, 0. So this fixed node, it is also having three row. First row, it is indicating the node. The second row, it is the degrees of freedom, and third row, it is indicating the value. The value we are setting as 0. That means that to node means that degrees of freedom corresponding to the first node will be 0 and 0. Okay. So that means it is fixed. Now we are giving some value, that E value, it is 1. Actually, it will be 1 multiplied by some weight factor. We are taking a steel, this cantilever beam, it is made of steel. So we are declaring here some basic variables. See here, the rho, it is 7850 kg per meter cube. Okay. The young modulus, it will be 1 multiplied by is 200 into 10 to the power 9. So that means the young modulus, it is 200 GPa. Okay. And new, we are defining 0.25. Poisson ratio, it is 0.25. Now, this is the basic value. Now, if we want to detect the damage position, first of all, we have to create the damage. So what we are doing here, artificially, we are reducing the E value of the some element. Okay. See here, for the 6th and the 24th positions, we are defining the value of E is equal to 0.7 and 0.8. Okay. 0.7 and 0.8 means 0.7 into 200 GPa will be there. It will be multiplied at that later. So we are reducing for the 6th element, we are reducing the 30% means E value. And for the 24th element, we are reducing the E value 20%. Okay, so we are creating the damage by reducing the E value. Okay, and after that, means this E value, it is stored in the E exact array. Okay, this E exact will pass to the different subroutine to calculate the global stiffness and global mass matrix, and after that, that too will be used to calculate the natural frequencies and mode shapes. And after that, in the MATLAB also we can means open a file where we can write all this input or output. Okay, so here with this command output out file 25, we are opening a file, a text file exact.txt, and in that file we are storing the value. Okay, exact value we are storing as an array format. Now what we are doing, first our target will be what? To create the natural frequencies and mode shapes with this damage locations also. Okay. Now with that, what we are doing, we are writing, we are calling a sub file. Okay, which is forward solution one. Okay, so this is it. This is an subscript. Okay, the main script, it is main.m, and this forward solution one actually it is an sub file. So here in the MATLAB, we can means for different operation, we can write different sub files also. Okay, so with this for means forward solution one, you can see it is a sub file, and here E exact we are passing as an input. Okay, and output will be what? The left hand side, all the variables will be the output: kg, mg, eigenvector reduced, eigenvalues. Okay, so all four means all these four are the output, and input for this forward solution one, this sub file, it is the E exact. Okay, so from this algorithm means from this main file, we will be passing E exact to this forward solution one sub file, and it will run and it will create this kg, mg, eigenvector reduced and eigenvalues. Okay. So first we'll see this forward solution one. Okay. So this is the forward solution one. Another, this is the sub file. Here, this at the first line, this input and output of this forward solution one, it is declared. So that see here, the name of the variable input and output variable, it is different. In the main, that when we are passing the variables, values of the variables, that input value, that name of the input value, it was E exact. Okay, but in the forward solution, it is the input, it is declared as CR. So that means you can change the name also in that individual subroutine or sub file. You can change the name also. So here in that individual subroutine, the input it is CR, the output it is K1, M1, V and D. Actually, it is the same. K1 means the kg, V1 means the K1, then M1 means the mg, the global mass matrix. Okay. Then V, it is the eigenvector reduced, and D, it is the eigenvalues. So from the main file, when we are calling the subroutine forward solution one, we are supplying some input and we are generating some output. And in the forward solution one, that subroutine, we are defining when the first line, we are defining the input and output, but the name can be different. So here also we are declining some global variables, okay, which will be used in different subroutines. And after that, the main target of this subroutine is what? To generate the stiffness, the global stiffness and the global mass matrix. Okay. So in these subroutines also, we are means we are calling another subroutine stiffness mass. Okay, this CR variable is actually the E values, a row of the array of the E values. It is passing uh, in this stiffness mass value, and with this stiffness mass subroutine, we are calculating the global stiffness and global mass. Okay. Then after that, what we are doing means we are actually uh, storing this kk and mk in another two matrices k1 and m1, reducing that rest means that restant degrees of freedom, means the first node in this cantilever beam, it is rested. So that means the first vertical degrees of freedom and the rotation degrees of freedom, it is rested. So that's why what we are doing here, that in that K1 and M1, we are eliminating the first row and the first column and the second row and the second column. So we are reducing that stiffness matrix. And after that, we are writing a command that EI means EIGS. Okay. And with this KK and M means K1 and M1, if we use this command EIGS, it will generate the natural frequencies and the mode shapes. Actually, it is an eigenvalue problem. So we are using this command EIGS. And we are getting V and D. V it is the vectors, means eigenvectors, and D it is the eigenvalues. Okay. So with this subroutine, we are getting the eigenvalues and eigenvectors, and after that, this with in that means by this subroutine forward solution, it will pass to this main subroutine uh, here, and it will be stored as an that global stiffness matrix will be stored as an Kg, global mass matrix will be stored as an Mg. Okay, and after that, we'll be getting the eigenvalues, the eigenvectors, and the eigenvalues. Okay. And what after that, what we are doing, we are actually means eigenvalues. It is actually, you know, that eigenvalues, it is the what? The square of the frequencies. So first of all, we are doing square root of these eigenvalues and getting the natural frequencies, and we are storing the eigenvectors. Okay. And after that, with this from line number 124 to 134, okay, you can see two for loops, and one for loops it is there. Okay. One main for loop it is there, and under that another for loops, another two for loop it is there. Actually, it is created to store the eigenvectors and to normalize the eigenvectors with the maximum values. Normalize means ultimately that plot will be showing the maximum value will be +1 to -1. So you may not do it. If you do it, then you will get the eigenvalues as a normalized eigenvalue, eigenvalue and eigenvector. So I have done this normalization. Okay. So for the means if I means if you do this normalization, you will get the plot for all the eigenvectors will be from -1 to +1. Okay. And you can see that if you want to plot these eigenvectors, the command it is means first I am opening a figure file, and then I am writing the plot eigenvectors of the first column. So it will plot the first eigenvector. Okay. Then similarly, I am means generating different figure file, figure 2, figure 3, figure 4, figure 5, and uh, uh, subsequently we are writing plot means plotting of the that second column of the eigenvectors variable, the third column, fourth column, and fifth column. So with this, we'll be generating the plot of the first five natural mode shapes. Okay. And after that, I have written the pause. Pause means if I run this algorithm, after running up to this that eigenvectors that up to that line 147, it will stop. It will pause, and we can see the figures. So first I will run it, then also means after that I will come the next part. So for running this program, you have to go to the editor portion and then run. So you can see here means that already the program run, and it is stopped here up to means line 149. And you can see the different figure. 5 figures has been generated. See here. So in these 5 figures, you can see the mode shapes. Okay. The first figure, figure 1, it is showing the first mode shapes of the cantilever beam. So
Yeah, yeah, the mode shape is not showing.
Huh? Can you see it now?
No, sir.
Oh, I have share. Okay, again I'll share. Okay. So can you see the figure 1 now?
Yes, sir.
Yeah, so
Yes,
this is
sir.
the plot, fast plot. Okay, it is showing the fast mode shape. So fast mode, so obviously it will start from the left hand end. The left hand end of the beam, it is the cantilever one. So that's why the value at this portion will be 0. And as I have normalized the mode shape, so maximum value it is 1. Okay, see here that that x along the x-axis the number of element has been shown, and along the y-axis the value of the mode shape has been shown. So when the value it is 30, means at the 30th element position the value of this mode shape it is 1. Okay, so minimum value it is 0 and maximum value it is 1. So this is the first figure. The second figure, can you see it, second figure?
Still in the first video.
Okay, actually one by one can I share? So can you see now that screen? All
Yes,
5
yes,
figures you can see. Okay,
yes.
so this is the figure
Yes.
1. The second figure it is the mode shape 2. Okay, mode shape 2 you can see that it starts from again 0 value from the left hand end, as it is a fixed cantilever, fixed hand end, left hand end, and the right hand side it is the free end. So it will have another turn or bend at, means you can say approximately at the middle. So this is the second mode shape. Okay. So first it will go from the 0 to some positive part, then it will come to the negative portion. The second mode shape. The third figure 3, it is indicating the third mode shape. Start from the 0, then it will go to positive portion, then it will again come back to negative, and after that it will go to the again positive part. You can see that maximum value it is in between -1 to +1. Okay. Why it is coming? Because we have normalized the mode shape. If we do not normalize the mode shape, then the value it will not be -1 to +1. You will be having some finite value. But you know that actually mode shape, that value it is not important. The shape it is the important. Okay. So that's why that all the mode shapes it is normalized, and the it is shown as the value has been shown from -1 to +1. Okay. And for the fourth figure 4, again another curvature increased. Okay, means another extra turn has been increased. Okay. So third means fourth and fifth we can see here. Okay. So that means what? That if you increase the now, means if you go from the first mode shape to fifth mode shape, what it is generating, that degree of what? Degree of complexity is increasing, or and plus minus curvature it is, means the whole length it is subdivided into more number of plus minus parts. Point of in okay, what counterflexure. So point of counterflexure is increasing. Okay, plus 2 minus points are increasing. So it is very easy. You know that's part that about the mode shapes. Basically, it is an eigenvalue problem. If you solve that equation, K means free vibration equation, K minus omega square m x equal to 0, then you will be getting the omega values. Omega it is corresponds to the natural frequencies. Okay, and x it is related to the mode shapes. So that's why in the MATLAB also we have used that EIGS command, EIGS command to solve the eigenvalue problem. So first, we are what we have done till now. First we will recall it. So first in this main routine, we have defined the basic means the variables like the length of the beam, depth and breadth of the beam, total number of element, total number of node, the degrees of freedom for the each node. Okay, the NDF, that means 2. Okay. Then after that we have generated the connectivity of the different elements. Okay, and after that we have generated the coordinate of the each node point. Then the next part, we have generated the means with this fixed node, we are generating the boundary condition. Boundary condition means the first node for this cantilever beam, the 2 degrees of freedom, first and second degrees of freedom, it is fixed. So that's why we are giving the 0 values, okay, for this 2 degrees of freedom. And after that, we have defined the E value, rho value, nu value, and created the 2 different damage. The 30% damage for the 6th element. For the 24th element, we are creating the 20% damage. And with this, we are storing these E values in a E exact array. The variable name is E exact. And after that, what we are doing, we are passing this E exact value in another subroutine, which is called forward solution 1. And in that with this help of this forward solution, we are solving the eigenvalue problem, and we are getting the eigenvalues and eigenvectors. Okay. In the forward solution 1, if you check, I have already discussed that first. Again, here we are calling another subroutine, stiffness mass, means for each element the E value will be passing, and for each element the element stiffness and element mass matrix will be generated. After that, the global mass and global stiffness matrix will be generated in this stiffness mass matrix. Okay, in that subroutine, and then it will be passed in this routine forward solution 1 by these 2 output KK and MK. Now with this KK and MK, we are we are eliminating the first row and the first column, and the second row and the second column, because the 2 degrees of freedom are restrained. So after that, we are uh, we are doing the eigenvalue analysis with this eigs command, and we are generating the eigenvalues and eigenvalues and eigenvectors. Okay, and after that, from this subroutine, we can get these values in that main subroutine, main routine actually, that main.m file, and here we are getting the value of the eigenvalues and the eigenvectors. And after that, we are normalizing the eigenvectors to have the plot between, means the maximum value will be +1 and the minimum value will be equal to -1. Okay, and after that we have plot that. Okay. Now means then we have paused that algorithm. Okay, and we have seen that 5 different eigen vectors, or you can say the mode shapes, normalized mode shapes. Up to that portion we have discussed. Now we'll be discussing the next part, that damage detection with the PSO. Okay, so with that, doing that, what we are doing here. So during the PPT presentations, I have told you that if we do the damage detection by numerical coding, so first we can do the FEM analysis to get the measured data. Okay, here our for free vibration analysis, our measurement data, it is the natural frequencies and mode shapes. Then actually in the real field, what happened in that measured data, measured natural frequencies and mode shapes, there will be noise. So simulate that exact behavior. What we can do here, we can add some noise. Okay, in the natural frequencies and mode shapes. So this portion, the line 204 to line 2012, this portion we are actually adding the noise. You can see here the noise addition declaration, means we are adding some noise in the natural frequencies and then mode shapes also. Okay. So that portion we can do, and how we are adding the noise, we are calling a random, a rand function. Rand function, actually this rand function, actually it creates the a random noise which follows the Gaussian distribution. Okay, so you can call it as a Gaussian white noise. So that noise we are calling it with this rand operation, and we are adding with different percentages. We can add, means say for frequency, generally in that paper, PSO paper, it is written that 0.15% in the natural frequency and 1 to 3% in the mode shapes. Okay. So that portion it is finished, means addition of the noise. After that, we'll be moving uh, towards the damage detection with PSO. Okay. So for that, first we have to generate a command fun. Okay. So with this fun, we are creating an objective function. Objective function is what actually we have discussed in that paper. It is the error between the natural frequencies and the mode shapes. So that we are creating with this objective obj, means this line 214. Okay. So with this subroutine objective COM1, what we are doing here, we are creating that objective function or error function. So we are sending, you can see here the input, it is the eigenvectors D and the frequency actual. That means we are passing the frequencies and the eigenvectors. Okay. And we are calculating the error of these two. One is for the error in the natural frequencies and the second is the error in the mode shapes. Okay. And then with this, we are in this main subroutine, we are getting that objective function. So with this objective function, now we'll be calling the particle sum optimization, that PSO algorithm to perform the means that optimization and detect the damage position. So to do that, we are declaring, first of all, to declare any algorithm, we have to means for running an algorithm, we have to declare some variables. Here also we are declaring some variables starting from the line 221. Okay, we are declaring the number of total variables for this algorithm. Here, the number of variables will be total number of element, because for each element there will be some damage. So each element it is varying. Okay, damage it is varying from 0 to 1. So that's why the total number it will be the number of element, and we are setting the lower limit. Lower limit it is 0.5. Okay, and upper limit it is 1. We can set this lower limit and upper limit, and this maximum iteration actually it are the maximum iteration, that n pop and toleration of the algorithms, we are setting different values. So these values will be used in the PSO algorithm. Okay, you can see that it is also shown with this percentage sign. So max iteration 1000 means maximum number of iterations. Population size, that n pop 75 means it is the swarm size of the particle swarm optimization. We are declaring it is an 75. Then the tolerance of the algorithm we are setting 10 to the power minus 8. We can directly write in that next to line, or either we can write as a variable also. Then the line 230, the options. Okay, optim options. With this command, we are calling the means means actually we are declaring the different variables. Okay, in that particle zone optimization. So different means in the particle zone optimization, different options are there. So to define that different options, we are means we are writing this command options equal to optim options. See here the particle swarm. The first it is written means we are using this particle swarm technique. The swarm size we are using 50. Okay, as we are declare before here, but we are not using. Okay, but here we are directly means defining that swarm size will be equal to 50. Maximum iteration will be equal to 2000. Directly we are defining. Then other factors are there. Okay, self adjustment weight 1.49, and another social adjustment factor it is there. We are defining at 1.49. So these value will be very means 1 to 1.5. Okay, these values. So here we have set the values as 1.49. Then objective limit, we have defined the total algo 1. So that value we have already defined, that it is 10 to the power minus 8. 10 to the power minus 8. Okay. And other factors like function tolerance, we have set 10 to the power minus 8. Maximum iterations it is 100. Okay. It is different. Maximum max total iteration it is different, but that iterations of the PSO algorithm it is defined previously, that maximum iteration equal to 2000. So that means before calling the PSO, we have to define the we have to define the different variables of the PSO algorithm. Okay, like the maximum iteration number, the swarm size of the PSO. Okay, the different adjustment weight adjustment factor, self adjustment weight factor that we have to define. Okay, and then we can call the particle swarm. Okay, that optimization technique with this line 232. So with this line 232, you can call the particle swarm optimization algorithm. And there also in the input right hand side in the bracket inputs are there, the lower value, upper value. These options also is passed as an input value. Okay, function value, number of variables. So all these are passed as an input, and output will be getting the x values. X values means the updated e value. Here x, this vector, it is showing the updated e value. The final means our final target. Okay, the damage position, which will be showing the damage position and quantification. So that portion will be running, and after that we'll be actually storing this. Means again I am opening an file eupdate.txt. It is an txt file, and we are storing that e exact value. Okay, in that means we are storing two array. First array it is indicating the e exact, and the second array it is indicating the updated e value. And next to line, that line 242, we are calculating the error norm. Error norm means the error between the means that actual damage position means the means we are up finally what finally we are detecting the damage locations, and we are storing in that e value, and we have the e exact value. So there will be error between the e value means e array and the e exact array. So e norm 1 will calculate the error between these two array. Okay, and next what we are doing, we are in the figure 2 we are plotting this e exact value. Okay, e exact value, and in that same plot we are using the hold on function. Hold on means in that same plot we'll be plotting the e updated e value, and at the last we are mentioning the talk. That means that it will show that after running this MATLAB it will show the total time. Okay, so you can see that after that pause I have actually put some enter. Okay, so as I have put the enter value, so the algorithm has already means if you give some pause option, means up to that point that algorithm will stop. Okay, in the MATLAB, and if we again put the enter, then it will again run, and it will run means up to the end. Okay, so that for my case the algorithm actually already learned, means it has already run, and you can see the final result. Okay, so can you see the final result? These two plot, the base the function value plot and the ultimately e plot, damage plot.
Yes, sir.
Yeah, so you can see the left side means left hand side figure. The figure, it is indicating the function value, means how the objective function it is reduced with respect to the iteration. When the x-axis showing the iteration, and y-axis it is showing the functional value. Functional value, the objective function that which we have defined the combination of the two part. One is the natural frequency and second is the error in the MAC value. Okay, so that value we are means it is reducing, and you can see that almost with only about you can see from this plot that uh, with only 100 to 150 iterations, the algorithm has almost reached zero values, zero functional value. And since we have run that this algorithm up to 200 2000 iteration, but you can see that means in 150 iterations only the algorithm reaches the zero value, zero functional value, almost zero functional value. Okay, and in the figure 2 you can see here the two part. that you can see that we have already given the damage in the 7th and the 24th location. Okay, so the blue line actually in this figure there are two lines, the blue line and the red line. Okay, the blue line it is showing the exact E value. Okay, so exact E value means what? It is showing that for other element the E it is 1, but for this 7th element the E value it is 0.7 because we have reduced that, okay, to create the damage. And for that 24th element the E value it is 0.8. You can see here the 0.8 value. For the 24th element we have created the damage with 0.8 into E, and for the 7th element we have created the damage with E value of 0.7 into E. So that blue line it is indicating the reference plot, and what the red line it is showing, red line it is showing the our final result. So you can see that our algorithm it is exact means it actually successfully detect the damage locations because two lines are almost matching. Okay, so that means that our algorithm is detecting the damage location and the damage location of the 7th and the 24th. Okay, as well as it also quantify that damage position. See exactly it is quantifying that at the 7th location the damage it is 30%. Okay, and at the 24th location the damage it is what? 80%. Okay, so you can see that PSO algorithm, even we have taken the 30 number of variables. Okay, the algorithm is capable of detecting the damage with very less iteration. Okay, not only the damage location as well as the quantification also. So algorithm has quantified the damage severity also. That means for the that 7th location, it has identified the location as well as quantify that there is a 30% of damage. Okay, and for the 24th location, it identifies the position because the two lines are matching. Okay, the actually the red line it is showing the algorithm's performance. Okay, the PS algorithm performance to detecting the damage position and the severity. So in the 24th locations also we can see that that it exactly quantifies the 20% damage of the 24th location. Okay. And these are about these two plots, and you can see the if you check this command window of the MATLAB, then you can see that E norm, the means the error norm of this uh, whole algorithm or whole performance, it is 0.002. That means very less error it is there. Okay, even less than the 2%. Okay, 0.2%, even less than the 0.2%. And the total elapsed time for running this algorithm it is 537.75 seconds. Okay, so how it is coming? Because we have at the start of the program we have written the tick, and the last we have written the talk. Okay, so this is the overall program, and actually if you want to learn this program in detail, then you have to learn how means I have not discussed in detail these portions like this subroutine, the stiffness mass. Stiffness mass is what? It is an subroutine which is taking the E value and other length and those things and creating the global stiffness and mass matrix. So if I open this file, you can see here stiffness mass. You can see that in the stiffness mass, some input it is coming. Elastic one is E value it is coming as an input, and output it is KLO and MLO, means that global stiffness and global mass matrix. So here what it is coming means what it is written here means for different element E value will be coming, and for each element the element mass matrix and element stiffness matrix will be generated. The size of the element mass and element stiffness matrix will be 4. This is for the standard beam element because for each node there will be 2 degrees of freedom, one vertical and one rotation. And we are taking a 2-noded beam element, so there will be 4 degrees of freedom. And this this is the standard formula for generating the element mass and element stiffness matrix. You can take from any FEM book. Okay, so that it depends upon the each element that E value, thickness value, mass value, and means density value. So according to that, mass and stiffness it is calculated, and after that you can see from the line 62 to 83, the global stiffness matrix has been generated. Means it will for loop, okay, has been created here. In that for loop, what is happening? There is this element stiffness matrix and element mass matrix. It is going, means it is storing in this KLO and MLO. KLO and MLO, it is the global stiffness and global mass matrix. So according to the connectivity, you can see here the connectivity, it is needed here. So according to the connectivity, nodal connectivity of the each member, the element stiffness matrix of the each element will stored into this global stiffness matrix, KLO and MLO. And with this, the KLO and MLO, that means global stiffness and global mass matrix will be generated, and it will be, it will again return back to this forward solution 1. Because in this forward solution 1, we are calling this means sub file, subroutine, stiffness mass. So KK and MK, that output, it actually provides the global stiffness matrix and global mass matrix. Then after that, we are applying the boundary condition. We are eliminating the first two rows and columns, and then we are calling the eigenfunction. Eigenfunction, what it is doing? It takes the global mass matrix and global stiffness matrix, and it solves the free vibration problem and eigenvalue problem, and generating the natural frequencies and the natural that mode shapes and the natural frequencies. And with this subroutine, that forward solution 1, we have called in this main one, line 1 and 3, 113. So in line 1 and 3, we have called this forward solution 1. So with this forward solution here, we are getting the eigenvalues and the eigenvectors. And after that, what we have done, we have normalized these eigenvectors, and then we have plot the 5 natural frequencies and mode shapes. So that values I have shown, that plots I have been shown, I have shown you. Okay. Then what we are doing, the forward problem, it is finished. At the starting of our presentations, I have shown you that to perform the damage detection, there is two problems. One is forward problem and one is inverse problem. So forward problem is up to getting the natural frequencies and mode shapes. Okay. Then after that, what we are doing, we are when starting the inverse problem. And in that inverse problem, we are using what you are using. We are first adding some noise to generate the simulated measurement data. And after that, we are using the PSO. Okay. In that PSO, first we are declaring some basic variables, swarm size, maximum iteration size, that self adjustment weight factor. Okay. So those we are declaring, then we are calling the particle swarm techniques. Okay. With the inputs, and we are getting the output X. So that X output, actually it is the E value, final updated E value. And then we are plotting this E exact and E value in the figure 2. Okay. And we are also calculating the error in this detection procedure. Okay. So, and finally that talk command. Okay. So that error norm, it is very less than 0.2%. And that plot I have already shown you, that plot it was there. Where is the other plot? Okay, maybe I have deleted. So you can see from this plot, this is the convergence history of this PSO. Okay, so with less, means very less iteration, say 150, the cost functional value, it is reducing to 0, and we are exactly means getting the damage locations at the 7th and the 24th positions, and we are also successfully quantifying the damage, means that 70% and the 80% damage of these two separate positions. So this is all about of means detecting the damage of a cantilever beam structure with PSO coding. Okay. So if you want to learn, first you have to learn means how to. It is very easy in MATLAB. You can see in other programs, in other language platform like Fortran or C. Okay, you have to write very in detail. For each part, you have to write in detail. But for in MATLAB, just you have to declare some basic variable. Okay, and if you want to declare some variable as a global, then you can declare as a global also. And to write means to write the basic FEM coding, first you have to generate either it may be beam structure or plate structure or different kind of structure. So first of all, you have to create the meshing means with that connectivity and the coordinates. Then you have to put the boundary condition. Okay, and after that, according to your solution, here I have used means we are solving only the free vibration problem. Okay, but if you want to solve the static problem or dynamic problem, so according to that you have to solve. Static problem means that k equal to p. If you want to solve that, then you have to again create the load vector. Okay, and you have to solve it to find out the displacement, and with that displacement you can then find out the strain or stress like that. Okay, and in dynamics problem and actual dynamics problem, you have to solve that the basic dynamics equation mx double dot plus cx dot plus kx equal to f, where f is a function of t. So that equation you have to solve. But here for this damage detection problem, we are solving only the free vibration problem, that k minus omega square m in bracket into x vector is equal to 0. Right hand side it is 0. So 0 force it is applied. And so that means we are solving here the eigenvalues and natural frequencies. Okay. And with that, we are detecting the damage position. So with this, I'm finishing this lecture. Okay. So if you have any question, you can ask related to that PPT and as well as this coding.
Participant side, do you have any queries? So which I will request you share this MATLAB code. Just try to simplify it and get all the
Okay,
unwanted part.
I'll actually share it because a lot of things are there. Okay.
Yes.
So I have to simplify it and then I'll share it. Okay.
So we are concluding this session. Thank you, Mr. Guchhait, for this interactive session. I hope our participants get some idea about that.
So means
Use of
here we have
AI.
used particle sum optimization. You can use any other technique
Yes.
in MATLAB, means anything neural network or CNN. It is available in MATLAB. So you can write your own coding.
Once you are master in one code, rest of the things we will observe very similar in nature. We can work in other method also. Okay, so thank you, Professor. We chat
Okay.
for the wonderful talk. Thank you.